We also have more navigation applications with these problems. These are like the problems we did previously that had to do with the law of sines and the law of cosines. Now we're just thinking in terms of vectors. So in this one, the ship leaves port on a bearing of 25 degrees. We know how far it travels, and then it turns due east and travels another 84.6 kilometers. We want to know how far the ship is from port and what its bearing from port is. So if we draw the picture, we've got our ship leaving with a bearing of 25 degrees. It travels 61.4 kilometers, and then it turns and travels straight east, and it goes for another 84.6 kilometers. Because of the way the problem was set up, we already had the tail to tip. That means our resultant vector is going to be the one that goes from the port to the current location of the ship. So this is our resultant vector right here. What we're trying to find out is how far the ship is from port, so that's going to be the magnitude of our resultant vector. And then for the bearing, we'll have to figure out how far it is from due north down to here. But first, let's find the magnitude or the length of this line segment. Well, we've got these two sides of our triangle. If we could figure out what this angle is, then we could use the law of cosines. Now we know this angle is 25 degrees. If we continue this line segment up here, then we've got also this angle up here is 25 degrees. This is a 90-degree angle. That means that this angle would be 65 degrees. From here around to here is 180 degrees. So to get this angle, we could take 180 degrees minus 65 degrees, and that gives us 115 degrees. Now this angle in here is 115 degrees. Now we've got the two sides and the angle in between them. We're trying to find this side, so we could use the law of cosines. I'm going to call this side D. So D squared would be 61.4 squared plus 84.6 squared minus 2 times 61.4 times 84.6 times the cosine of 115 degrees. If we work all that out, we get something like this for D squared. Then we take the square root of both sides to get our approximate answer for the distance, which is 123.8 kilometers. Then the next thing we want to find is the bearing of where the ship is from port at this point. So we already know that from here to here is 25 degrees. We need to know what this angle is. So we need to know angle theta, and then our bearing will be that angle plus the 25 degrees. So if we look at the triangle, we know the side opposite that angle, and then we have this side and the angle opposite, so we can use the law of sines to find theta. We'd have 84.6 over the sine of theta would equal 123.8 over the sine of 115. If we solve this for the sine of theta, we'd have 84.6 times the sine of 115 divided by 123.8. Once we get that value, we're going to use inverse sine to solve for theta, and it turns out that theta is approximately 38.3 degrees. So to get our bearing, we're going to take 38.3 degrees and add that to 25. That gives us a bearing of 63.3 degrees. The last example has to do with the airspeed and the ground speed of a plane. So the airspeed is the speed of the plane relative to the air. In other math classes you've had, they might have talked about the speed of the plane in still air. That's the same thing as the airspeed. The ground speed is the speed relative to the ground. So that's the actual speed that the plane would be going if you were measuring it against the ground. The ground speed is actually the sum of the airspeed and the wind speed vectors. If this was our airspeed of our plane here, and then we had our wind vector here, what it would be doing is blowing the plane this direction. So this would be the airspeed vector. This is the wind vector. And then the resultant of those two is the ground speed. So this one over here is the ground speed vector. So in this example, we've got a plane that's going at a bearing of 70 degrees with an airspeed of 230 miles per hour. Both of these are talking about the airspeed vector. And this time we're talking about a vector that represents velocity. So this is talking about our airspeed as a velocity. It's got a direction and it's got a magnitude. So this is our magnitude, and this is going to tell us our direction. Then we're also going to have a wind speed vector that has a magnitude of 25 miles per hour, and this tells us the direction. So what we're going to find is the resultant vector of those two, and we want to know both the direction and the magnitude. For this picture, our bearing for the plane is 70 degrees. So that would mean the angle from here to here is 70 degrees. And then this magnitude of this vector is going to be our speed, which is 230 miles per hour. So this is our airspeed vector. And then in these ones, you have to be really careful with the wording when it talks about the wind. This says the wind is blowing from a direction of 310 degrees. So if we look at 310 degrees as a bearing in our picture, that would be from here all the way around to here would be 310 degrees. But this is saying that it's blowing from a direction of 310 degrees. So actually the wind is blowing the opposite direction of that. So it's blowing this direction, and the magnitude of this one is 25 miles per hour. So it's a much shorter vector than this one. So this would be our wind speed vector. What we're trying to find is the resultant vector of the airspeed and the wind speed. We could do our parallelogram, and this would be our ground speed vector. We're going to have to figure out some things about the angles for this one. First of all, if you look at this vector that we had drawn over here, this was 310 degrees from straight north. So the angle from here back to straight north would be another 50 degrees to get to a full 360 degrees. So that's 50 degrees. And what that means, if we use the fact of vertical angles, if this is 50 degrees, then this down here is a vertical angle. So that makes this angle 50 degrees also. And then we know that this angle is 70 degrees. From here all the way around to here is a full 180 degrees. So to find this angle of the parallelogram right here, we want to take our 50 and our 70 and add those together and then subtract that from 180. That tells us that the angle in here is 60 degrees. Now, since we have that angle, we can do this by using the law of cosines. Since this side of our parallelogram was 25, then this side is also, and this angle and this angle are supplements, so that means this one 120 degrees. Now we've got two sides and the angle in between them, and we're trying to find this side. So let's call this g for ground speed. So g squared would equal 230 squared plus 25 squared minus 2 times 230 times 25 times the cosine of 120 degrees. That's going to turn out to be 59,275, and we're going to take the square root of both sides to get our ground speed magnitude, and that's going to be approximately 243. And this is our ground speed magnitude, so this is actually in miles per hour. Then to find the bearing for the ground speed, That's going to be our 70 degrees here plus this little angle of the triangle. So we want to find this angle and add it to the 70 degrees to get our bearing. Now in this triangle we already know some lengths and angles, so we can use the law of sines. We would have 25 over the sine of theta, which would equal 243 over the sine of 120. Now if we work this out and solve it for theta, theta ends up to be approximately 5 degrees. So then to get our bearing, we're going to take the 70 degrees here plus the 5 degrees here. And that would give us 75 degrees for the bearing.